Deep in the vast expanse of our universe exists something so extraordinary, so fundamentally bizarre, that it challenges every assumption we have about the nature of reality itself. We're talking about neutron stars, objects so dense that a single teaspoon of their material would weigh 6 billion tons. To put that in perspective, imagine taking Mount Everest, crushing it down to the size of a sugar cube, and then making it 10 times heavier. That's what we're dealing with when we examine neutron star matter. These cosmic enigmas represent the most extreme physics laboratory the universe has to offer. They're the remnants of stellar catastrophes so violent they can outshine entire galaxies containing hundreds of billions of stars. Yet, despite their incredible brightness during formation, neutron stars themselves are surprisingly small, typically only about 12 miles across, roughly the size of Manhattan. Within that compact space, however, lies matter compressed to densities that exceed even the nucleus of an atom. What makes neutron stars truly mind-bending isn't just their incredible density. These objects possess magnetic fields so powerful they could strip the information from every credit card on Earth from a distance of 600 miles. Some neutron stars rotate at speeds that defy comprehension, completing 700 full rotations every single second. Imagine a sphere the size of a city spinning faster than the blades of a helicopter, and you begin to grasp the sheer impossibility of what we're discussing. The story of neutron stars begins with a fundamental question about the life cycle of massive stars. When we look up at the night sky, we see stars that appear eternal and unchanging. But appearances can be deceiving. Stars are actually engaged in a constant battle between two opposing forces, the outward pressure from nuclear fusion trying to blow them apart, and the inward pull of gravity trying to crush them down. For most of a star's life, these forces exist in perfect balance. But for the most massive stars in the universe, those at least 8 times heavier than our Sun, this balance is destined to fail in the most spectacular way possible. The journey toward neutron star formation begins during the final moments of a massive star's life. Throughout its existence, the star has been steadily fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. Each fusion reaction releases tremendous amounts of energy that keep the star shining and provide the outward pressure necessary to resist gravitational collapse. But there's a limit to this process. When the star's core begins producing iron, something catastrophic happens. Iron represents a unique turning point in stellar evolution because it cannot be fused into heavier elements while releasing energy. Instead, iron fusion actually absorbs energy, removing the very force that has been keeping the star stable. Without the outward pressure from fusion reactions, gravity suddenly gains the upper hand. The star's core, which contains more mass than our entire Sun, begins to collapse under its own weight. This collapse happens with breathtaking speed. In less than a second, the core shrinks from roughly the size of Earth to something no bigger than a city. The density increases so rapidly that electrons and protons are literally crushed together to form neutrons. This process, called neutronization, creates matter so dense that a chunk the size of a dice would weigh as much as a cruise ship. The collapse releases more energy in a single second than our Sun will produce over its entire 10 billion-year lifetime. The core collapse triggers a supernova explosion that represents one of the most energetic events in the known universe. The explosion is so brilliant it can be seen from billions of light-years away. temporarily outshining the combined light of every star in its host galaxy. The blast wave carries away the star's outer layers at speeds of up to 30,000 miles per second, enriching the surrounding space with heavy elements that will eventually form new stars, planets, and potentially life itself. But the most remarkable part of this story is what gets left behind. The collapsed core, now composed almost entirely of neutrons, has become something unprecedented in the universe, a neutron star. These objects represent matter compressed to the very limits of what physics allows. They're so dense that if you could somehow transport a neutron star to Earth and place it in your backyard, its gravitational pull would be so strong that it would drag you toward it at an acceleration of 200 billion times Earth's gravity. Understanding neutron stars requires us to abandon our everyday intuitions about how matter behaves. On Earth, we're familiar with matter in its ordinary forms: solids, liquids, gases and plasmas. But neutron stars exist in a regime where matter behaves according to rules we're only beginning to understand. The pressures and densities involved are so extreme that they can only be approximated in the most powerful particle accelerators, and even then, only for the briefest moments. The magnetic fields surrounding neutron stars are equally extraordinary. Earth's magnetic field, which protects us from harmful solar radiation, measures about half a Gauss. A refrigerator magnet produces a field of about 100 Gauss. The most powerful magnetic fields created in laboratories reach about 45 Tesla, or 450,000 Gauss. Neutron stars laugh at these numbers. Their magnetic fields typically measure between 100 million and 1 trillion Gauss. At these field strengths, the very structure of atoms begins to change. Electrons are forced into cigar-shaped orbits, and matter itself becomes magnetically polarized. The rotation of neutron stars adds another layer of impossibility to their already extreme nature. Some neutron stars, called millisecond pulsars, complete one full rotation in just a few milliseconds. To appreciate this speed, consider that a point on the surface of such a neutron star would be moving at roughly 20% the speed of light. At these velocities, the star's shape becomes noticeably distorted, bulging outward at the equator due to centrifugal forces. These rapidly spinning neutron stars often emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep through space like lighthouse beams, creating the regular pulses that give pulsars their name. The timing of these pulses is so precise that the most stable pulsars keep time more accurately than the best atomic clocks on Earth. This remarkable regularity has made pulsars invaluable tools for testing our understanding of physics under extreme conditions. The discovery of neutron stars represents one of the greatest triumphs of theoretical physics. Their existence was predicted in 1934, just 2 years after the discovery of the neutron itself. Scientists calculated that under the right conditions, matter could be compressed to such extraordinary densities that it would consist almost entirely of neutrons. For over 30 years this remained purely theoretical until 1967, when astronomers detected the first pulsar signals. The detection of pulsars initially puzzled astronomers so much that they were briefly nicknamed little green men signals because of their artificial-seeming regularity. It wasn't until scientists realized these signals were coming from rapidly rotating neutron stars that the true nature of these objects became clear. The confirmation of neutron stars validated decades of theoretical work and opened up entirely new fields of astrophysics. What makes neutron stars truly fascinating isn't just their extreme properties, but what they can teach us about the fundamental nature of matter and energy. These objects exist at the intersection of several branches of physics: nuclear physics, quantum mechanics, general relativity, and thermodynamics all play crucial roles in determining their structure and behavior. By studying neutron stars, we're essentially conducting experiments in physics that would be impossible to perform on Earth. The quest to understand what lies inside neutron stars has driven some of the most ambitious scientific projects of our time. Space-based observatories like the Neutron Star Interior Composition Explorer have been designed specifically to peer inside these objects. Ground-based gravitational wave detectors have opened up entirely new ways of studying neutron star collisions. Advanced computer simulations now allow us to model the behavior of matter under conditions that exist nowhere else in the universe. As we stand on the threshold of revolutionary discoveries about neutron stars, we're about to embark on a journey that will take us from the explosive deaths of massive stars to the very heart of matter itself. We'll explore how these cosmic laboratories challenge our understanding of physics, reveal the existence of exotic forms of matter that may not exist anywhere else in the universe, and provide insights into the fundamental nature of reality itself. The story of neutron stars is ultimately a story about the limits of physics and the incredible creativity of the universe in pushing matter and energy to their absolute extremes. These objects represent nature's most successful attempt to compress as much mass as possible into the smallest possible space without creating a black hole. They're cosmic experiments in the behavior of matter under conditions so extreme that they stretch our theories to their breaking point. In the following chapters, we'll peel back the layers of these cosmic enigmas, starting with their violent birth in supernova explosions and working our way down to their mysterious cores, where the very nature of matter itself may be transformed into something unrecognizable. We'll discover how neutron stars have become cosmic laboratories that are helping us understand everything from the behavior of matter at nuclear densities to the nature of space and time itself. The journey ahead will challenge everything you think you know about the physical world. We'll encounter matter so dense it defies imagination, magnetic fields that could tear apart atoms, and rotation speeds that push the very fabric of space-time to its limits. By the end of this exploration, you'll understand why neutron stars represent some of the most extreme and fascinating objects in the entire universe, and why their secrets continue to drive the cutting edge of modern physics. Chapter 1. The Birth of a Neutron Star. The universe operates on a scale that dwarfs human comprehension, yet some of its most profound mysteries can be understood by examining a single fundamental struggle that plays out over millions of years. Every star in the night sky is locked in an epic battle between two of nature's most powerful forces. On one side stands nuclear fusion, the process that powers stars and creates the energy that makes them shine. On the other side lurks gravity, the relentless force that seeks to crush everything down to a single point. For most stars, this battle reaches a peaceful resolution. For the universe's most massive stars, however, this cosmic wrestling match ends in one of the most violent and spectacular events imaginable. Understanding how neutron stars form requires us to first appreciate the sheer scale and violence of the stellar deaths that create them. These aren't gentle transitions like the death of our sun, which will eventually expand into a red giant and then quietly fade away as a white dwarf. The stars that become neutron stars are stellar monsters, objects containing at least 8 times the mass of our Sun, and often much more. These massive stars live fast and die young, burning through their nuclear fuel at rates so prodigious that they exhaust their energy reserves in mere millions of years, rather than the billions of years that smaller stars enjoy. The life and death of massive stars. Massive stars represent the universe's most extravagant energy producers. While our Sun fuses about 600 million tons of hydrogen into helium every single second, the most massive stars consume their fuel at rates thousands of times faster. This incredible energy output is what allows them to maintain their structure against the crushing force of their own gravity. The more massive a star becomes, the hotter and denser its core must be to generate enough outward pressure to prevent gravitational collapse. The life story of a massive star reads like a cosmic tragedy in multiple acts. During its main sequence phase, the star fuses hydrogen into helium in its core, just like our Sun does. But because of the star's enormous mass, this process occurs at temperatures exceeding 40 million degrees Celsius, nearly 3 times hotter than the Sun's core. The nuclear reactions proceed so rapidly that the star burns through its hydrogen reserves in perhaps 10 million years, compared to the Sun's leisurely 10 billion-year hydrogen-burning phase. Once the hydrogen in the core is exhausted, the star faces its first crisis. Without the outward pressure from hydrogen fusion, gravity begins to compress the core. This compression raises the temperature and density until a new nuclear reaction becomes possible: helium fusion. The star now begins converting helium into carbon and oxygen, but this process requires even higher temperatures and pressures than hydrogen fusion. The core temperature climbs to over 100 million degrees Celsius, and the star's energy output increases dramatically. The helium-burning phase lasts only about 1 million years for a typical massive star. When the helium is exhausted, the cycle repeats. The core contracts again, temperatures rise, and carbon begins fusing into heavier elements like neon and magnesium. Each successive fusion stage requires higher temperatures, lasts for shorter periods, and produces less energy per unit mass of fuel consumed. The star is literally burning through its reserves at an accelerating pace, like a car with a fuel leak driving faster and faster to reach its destination. Carbon burning might last only 1,000 years. The subsequent neon burning phase endures for perhaps just 1 year. Oxygen burning, which creates silicon and sulfur, may last only 6 months. With each stage, the star's core becomes increasingly unstable, and the end approaches with frightening speed. The star has become a cosmic time bomb, and the countdown is accelerating. Throughout this process, the star develops a layered structure resembling a cosmic onion. The outermost layers continue burning hydrogen, while deeper layers burn helium, carbon, neon and oxygen in successive shells. At the very center, the core grows increasingly dense and hot as it accumulates the products of these fusion reactions. The star's surface may swell to enormous proportions. Some become so large they would engulf the orbit of Jupiter if placed in our solar system. The final stage of this stellar evolution arrives when the core begins producing iron. Iron occupies a unique position in the periodic table because it represents the most tightly bound nucleus. Fusing elements lighter than iron releases energy, while fusing elements heavier than iron actually requires energy input. When a massive star's core reaches this point, it has essentially hit a wall. The nuclear reactions that have powered the star for millions of years can no longer provide the energy needed to resist gravitational collapse. The accumulation of iron in the core proceeds rapidly. Within days or weeks, the core mass approaches what physicists call the Chandrasekhar limit, approximately 1.4 times the mass of our Sun. At this point, the core can no longer support its own weight through the quantum mechanical pressure of electrons. The stellar core has reached a point of no return, and what happens next occurs so quickly that it defies human comprehension. The supernova, a star's explosive end. The core collapse of a massive star represents one of the most dramatic events in the universe. When the iron core exceeds the Chandrasekhar limit, it begins to collapse under its own gravity at speeds approaching 70,000 kilometers per second, roughly 23% the speed of light. The collapse is so rapid that the core, originally about the size of Earth, shrinks to a sphere only 20 kilometers in diameter in less than 1 second. During this collapse, the core's density increases by a factor of 100 trillion. The protons and electrons in the core are literally crushed together to form neutrons, a process that requires enormous amounts of energy. The gravitational potential energy released during this collapse is almost incomprehensible, equivalent to the energy our Sun will produce over its entire 10 billion-year lifetime, but released in a single second. The collapse continues until the core reaches nuclear density, approximately 400 trillion times denser than water. At this point, the nuclear force, which binds protons and neutrons together in atomic nuclei, finally becomes strong enough to halt the collapse. The core suddenly becomes incompressible, like a ball bouncing off a concrete wall. The infalling material rebounds violently, creating a shock wave that propagates outward through the star. This shock wave encounters the star's outer layers, which are still falling inward at tremendous speeds. The collision between the outbound shock wave and the infalling material creates conditions of unimaginable violence. Temperatures soar to over 100 billion degrees Celsius, thousands of times hotter than the Sun's core. The shock wave accelerates the outer layers of the star to speeds exceeding 30,000 kilometers per second, launching them into space in a spectacular explosion known as a supernova. The energy released in a supernova explosion is so enormous that it can outshine an entire galaxy containing hundreds of billions of stars. The explosion is visible from distances of billions of light-years, making supernovae among the most luminous events in the universe. The blast wave carries away roughly 99% of the star's mass, enriching the surrounding interstellar medium with heavy elements that were forged in the star's core and during the explosion itself. The supernova explosion serves as one of the universe's most important manufacturing processes. Elements heavier than iron, including gold, platinum and uranium, are primarily created during the intense conditions of the explosion. The incredible temperatures and pressures allow nuclear reactions that would be impossible under normal stellar conditions. These heavy elements, along with the lighter elements created during the star's lifetime, are dispersed throughout space by the explosion, eventually becoming incorporated into new stars, planets, and potentially life itself. The shock wave from the supernova continues to expand for thousands of years, creating beautiful nebulae that glow with the light of heated gas. These supernova remnants serve as cosmic laboratories where astronomers can study the aftermath of stellar explosions. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that was observed by Chinese astronomers in 1054 AD. The explosion was so bright it was visible during daylight, for 23 days. The neutrinos produced during the core collapse provide another fascinating aspect of supernova. During the neutronization process, when protons and electrons combine to form neutrons, vast numbers of neutrinos are produced. These nearly massless particles interact so weakly with matter that they can escape from the dense core immediately, carrying away about 99% of the explosion's energy. In the few seconds during which a supernova occurs, it produces more neutrinos than all the stars in the observable universe combined. The detection of neutrinos from supernovae has provided crucial insights into these explosive events. In 1987, astronomers detected neutrinos from supernova 1987A in the Large Magellanic Cloud, confirming theoretical predictions about the core collapse process. The neutrinos arrived at Earth several hours before the optical light from the explosion, because they escaped immediately from the core while the light had to work its way through the star's outer layers. From ashes to Enigma, the creation of a neutron star. While the supernova explosion disperses most of the star's mass into space, the collapsed core remains behind as a neutron star. This stellar remnant represents one of the most extreme objects in the universe. A sphere roughly 20 kilometers in diameter containing between 1.4 and 2.1 times the mass of our Sun. The matter in a neutron star is compressed to densities that exceed those found in atomic nuclei, creating a state of matter that exists nowhere else in the universe. The formation of a neutron star requires a delicate balance. If the original star is too massive, the core collapse will not halt at nuclear density, and the object will continue contracting to form a black hole. If the star is not massive enough, the core will stabilize as a white dwarf, rather than undergoing complete collapse. Only stars within a specific mass range, typically between 8 and 25 times the mass of the Sun, produce neutron stars. The neutronization process that occurs during core collapse represents one of the most dramatic phase transitions in nature. Under normal conditions, protons and electrons maintain their separate identities, held apart by electromagnetic forces. But when matter is compressed to densities exceeding 1,000 trillion grams per cubic centimeter, these particles can no longer remain separate. The electromagnetic force becomes overwhelmed by the extreme conditions, and protons and electrons are forced together to form neutrons. This process requires enormous amounts of energy because it works against the electromagnetic repulsion between protons. The energy comes from the gravitational collapse itself, which releases enough energy to power the neutronization reaction and drive the supernova explosion. The resulting neutron star is composed almost entirely of neutrons, with only a small fraction of protons and electrons remaining in equilibrium. The structure of a newly formed neutron star is unlike anything else in the universe. The surface gravity is approximately 200 billion times stronger than Earth's gravity. This means that a marshmallow dropped from a height of 1 meter onto a neutron star's surface would impact with the energy of an atomic bomb. The escape velocity from a neutron star's surface is roughly 100,000 kilometers per second, about 1/3 the speed of light. The magnetic field of a neutron star is equally extraordinary. During the core collapse, the original star's magnetic field becomes concentrated into a much smaller volume, amplifying its strength by factors of trillions. The resulting magnetic field is typically between 100 million and 1 trillion times stronger than Earth's magnetic field. These magnetic fields are so intense that they can affect the structure of atoms themselves, forcing electrons into highly elongated orbits. The rotation of neutron stars provides another remarkable characteristic. Due to conservation of angular momentum, the slowly rotating core of the original star speeds up dramatically as it collapses. Just as a figure skater spins faster when pulling in their arms, the collapsing stellar core accelerates its rotation. Some neutron stars rotate hundreds of times per second, completing one full rotation in just a few milliseconds. The temperature of a newly formed neutron star is almost beyond comprehension. The core collapse and neutronization process heat the neutron star to temperatures exceeding 1 trillion degrees Celsius. At these temperatures, the neutron star glows primarily in high-energy radiation, like X-rays and gamma rays. Over time, the neutron star cools by radiating this energy away, but the cooling process takes millions of years. The creation of a neutron star marks the birth of an object that will persist for trillions of years. Unlike ordinary stars, which eventually exhaust their nuclear fuel and die, neutron stars have no ongoing energy source beyond their initial thermal energy and rotational energy. They will slowly cool and spin down over cosmic timescales, eventually becoming cold, dark objects that persist long after all the ordinary stars in the universe have burned out. The process of neutron star formation represents one of nature's most successful attempts to compress matter to its absolute limits. The densities achieved in neutron stars approach those found in atomic nuclei, representing the highest stable densities of matter in the universe. Only black holes achieve higher densities, but at the cost of disappearing behind an event horizon where the laws of physics, as we understand them, break down. Understanding neutron star formation has required some of the most sophisticated theoretical work in modern physics. The process involves nuclear physics, quantum mechanics, general relativity, and thermodynamics, all operating simultaneously under the most extreme conditions imaginable. The successful prediction of neutron star existence made decades before their discovery represents one of the greatest triumphs of theoretical physics. The formation process also explains why neutron stars are relatively rare objects. The specific conditions required for neutron star formation, a star massive enough to undergo core collapse but not so massive as to form a black hole, occur only for a small fraction of all stars. Astronomers estimate that only about 1% of all stars will eventually become neutron stars, making them among the rarest objects in the universe. The birth of a neutron star through supernova explosion represents just the beginning of its story. These cosmic remnants possess properties so extreme that they challenge our understanding of physics and serve as natural laboratories for studying matter under conditions that cannot be reproduced on Earth. The violent process that creates them is merely the first chapter in a tale that will explore the very limits of what matter and energy can achieve in our universe. Chapter 2. The extreme physics of neutron stars. The moment a neutron star forms, it becomes the most extreme object in the known universe. To truly appreciate what we're dealing with, we need to understand that neutron stars push the boundaries of physics so far beyond our everyday experience that they seem to operate by entirely different rules. These objects possess properties so extraordinary that they challenge our fundamental understanding of how matter, energy, space, and time behave under the most extreme conditions imaginable. Density beyond imagination. The density of neutron star matter represents one of the most mind-bending concepts in all of physics. When we talk about density, we're discussing how much mass is packed into a given volume of space. Water has a density of 1 gram per cubic centimetre, which means a sugar cube of water weighs exactly 1 gram. Lead, one of the densest materials we commonly encounter, has a density of about 11 grams per cubic centimetre. The densest material found naturally on Earth is osmium, with a density of 22 grams per cubic centimetre. Neutron star matter obliterates these numbers completely. The material in a neutron star's core reaches densities of approximately 500 million tons per cubic centimetre. This means that a single sugar cube of neutron star material would weigh roughly the same as Mount Everest. To put this in perspective, if you could somehow compress all the water in Earth's oceans into a space the size of a marble, you would still fall short of neutron star density by a factor of several thousand. The physics behind this incredible density lies in the fundamental structure of atoms themselves. Under normal conditions, atoms consist mostly of empty space. The nucleus, containing protons and neutrons, occupies an incredibly tiny fraction of the atom's volume, while electrons orbit at relatively vast distances. If an atom were the size of a football stadium, the nucleus would be smaller than a marble sitting at the center of the field. All the rest is essentially empty space. In neutron star matter, this empty space has been completely eliminated. The immense gravitational pressure has crushed atoms so thoroughly that electrons have been forced to merge with protons, creating neutrons. These neutrons are then packed together so tightly that they're essentially touching, creating a state of matter where the normal structure of atoms has been completely destroyed. The result is a material where nuclear density matter extends continuously throughout the object. This extreme density creates gravitational effects that are almost impossible to comprehend. The surface gravity of a typical neutron star is approximately 200 billion times stronger than Earth's gravity. This means that if you could somehow stand on the surface of a neutron star, you would weigh as much as 200 billion people combined. A paper clip dropped from a height of 1 meter would hit the surface with the energy of a nuclear bomb. The gravitational field is so intense that it noticeably affects the flow of time itself, causing clocks to run slower compared to those in weaker gravitational fields. The density also affects light in remarkable ways. Photons trying to escape from the neutron star's surface must work against the immense gravitational field, losing energy in the process. This gravitational redshift means that light appears redder and dimmer than it would if the same source were located in a region of weaker gravity. The effect is so pronounced that it must be accounted for in all observations of neutron stars. Magnetism stronger than anything known. The magnetic fields surrounding neutron stars represent another aspect of their physics that defies our everyday understanding. To appreciate just how powerful these fields are, we need to understand magnetic field strength in terms of Gauss or Tesla. Earth's magnetic field, which protects us from harmful solar radiation and allows compass needles to point north, measures about 0.5 Gauss at the surface. A typical refrigerator magnet produces a field of about 100 Gauss. The most powerful continuous magnetic fields created in laboratories reach about 45 Tesla, or 450,000 Gauss. Neutron stars make these numbers look pathetically weak. A typical neutron star possesses a magnetic field strength of about 100 million to 1 trillion Gauss. The strongest magnetic fields ever detected from neutron stars, found in objects called magnetars, can reach 1,000 trillion Gauss. These fields are so powerful that they would be lethal to any form of life from a distance of 600 miles, not through direct magnetic effects, but by disrupting the biochemical processes that keep living cells functioning. The origin of these incredible magnetic fields lies in the physics of the neutron star's formation. When the original star's core collapses, any magnetic field that was present gets compressed along with the matter. Just as a figure skater spins faster when they pull their arms inward, the magnetic field becomes concentrated and amplified as the star shrinks. A magnetic field that might have been comparable to the Sun's field in the original star becomes amplified by factors of billions or trillions during the collapse. These magnetic fields have profound effects on the behavior of matter near neutron stars. In the presence of such strong fields, atoms themselves become distorted. Electrons, which normally occupy spherical or dumbbell-shaped orbitals around atomic nuclei, are forced into thin, cigar-shaped orbits aligned with the magnetic field. This effect, called magnetic polarization, fundamentally changes how atoms interact with light and with each other. The magnetic field also affects the neutron star's surface in dramatic ways. Charged particles near the surface are forced to move along the magnetic field lines, creating intense beams of radiation that shoot out from the star's magnetic poles. These beams often don't align with the star's rotation axis, causing them to sweep through space like lighthouse beams as the star spins. The energy powering these beams comes from the neutron star's rotational energy, gradually slowing the star's spin over millions of years. In the most extreme cases, neutron stars called magnetars have magnetic fields so powerful that they can cause the star's crust to crack and shift. These starquakes release more energy in 1/10 of a second than the Sun produces in 100,000 years. The magnetic field stores so much energy that it can actually heat the neutron star's surface to millions of degrees, making magnetars glow brightly in X-rays even though they may be millions of years old. Rotation speeds that defy belief. The rotation rates of neutron stars push the boundaries of what seems physically possible. While our Sun rotates once every 25 days, and Earth completes one rotation every 24 hours, neutron stars can spin at rates that challenge our understanding of how fast a solid object can rotate without tearing itself apart. The fastest spinning neutron stars, called millisecond pulsars, complete one full rotation in just a few milliseconds. The record holder, designated PSRJ 1748-2446 AD, spins 716 times per second. To truly appreciate these rotation rates, consider what they mean for the neutron star's surface. A point on the equator of this record-holding pulsar is moving at approximately 24% the speed of light. At such velocities, the effects of Einstein's special relativity become significant. Time dilation occurs, space contracts, and the very geometry of space-time around the star becomes warped by the combination of intense gravity and rapid rotation. The physics of neutron star rotation involves a delicate balance between centrifugal force trying to tear the star apart and gravity trying to hold it together. As a neutron star spins faster, material at its equator experiences increasingly strong centrifugal forces. If the star were to spin just slightly faster than the current record holder, the centrifugal force would overcome gravity and the star would begin to shed material from its equator. This represents the absolute speed limit for neutron star rotation. The origin of these incredible rotation rates lies in the conservation of angular momentum during the star's formation. When the original star's core collapses from a diameter of thousands of miles to just a few miles, its rotation rate must increase dramatically to conserve angular momentum. This is the same principle that causes a figure skater to spin faster when they pull their arms inward, but taken to an extreme that has no parallel in our everyday experience. Many neutron stars are born spinning rapidly, but they gradually slow down over time as they lose energy through various processes. The magnetic field plays a crucial role in this spin-down process. Charged particles trapped in the magnetic field are accelerated to high speeds, carrying away energy and angular momentum. This electromagnetic braking gradually reduces the neutron star's rotation rate over millions of years. However, some neutron stars can actually spin up rather than slow down. This happens when the neutron star is part of a binary system with a normal star. Material from the companion star can fall onto the neutron star's surface, and the conservation of angular momentum from this infalling material can cause the neutron star to spin faster. This process, called accretion, is responsible for creating the millisecond pulsars that represent the fastest spinning objects in the universe. The rapid rotation of neutron stars also affects their shape in measurable ways. The centrifugal force causes the star to bulge outward at the equator, creating an oblate spheroid rather than a perfect sphere. For the fastest spinning neutron stars, this oblateness becomes quite pronounced, with the equatorial radius being several % larger than the polar radius. This deformation affects the star's gravitational field and can be detected through precise timing measurements of pulsar signals. Pulsars, lighthouses of the cosmos. Pulsars represent one of the most remarkable phenomena in astronomy and provide us with our primary means of studying neutron stars. These objects are essentially neutron stars that emit beams of radiation from their magnetic poles, and as the star rotates, these beams sweep through space like lighthouse beams. When one of these beams points toward Earth, we detect a pulse of radiation. The regularity of these pulses has made pulsars some of the most precise timekeepers in the universe. The discovery of pulsars in 1967 initially puzzled astronomers so much that the first pulsar signals were nicknamed Little Green Men because of their artificial seeming regularity. Graduate student Jocelyn Bell Burnell noticed unusual rapidly repeating signals while analyzing data from a radio telescope designed to study quasars. The signals appeared to pulse with a period of 1.337 seconds, more regular than any known astronomical phenomenon. It wasn't until additional pulsars were discovered that astronomers realized these signals were coming from rapidly rotating neutron stars. The physics behind pulsar emission involves the complex interaction between the neutron star's magnetic field and charged particles in its vicinity. The neutron star's magnetic field creates a magnetosphere, a region of space where the magnetic field dominates over other forces. Charged particles become trapped in this magnetosphere and are accelerated to enormous speeds along the magnetic field lines. These particles emit radiation as they spiral around the magnetic field, creating intense beams that emerge from the star's magnetic poles. The beams are incredibly narrow, typically only a few degrees wide, and they sweep through space as the neutron star rotates. This creates the lighthouse effect that gives pulsars their name. The intensity of the radiation in these beams is extraordinary. A typical pulsar beam contains more energy than the total output of thousands of stars, like our Sun, all concentrated into a cone just a few degrees wide. The regularity of pulsar timing is truly remarkable. The most stable pulsars maintain their pulse periods with an accuracy that rivals or exceeds the best atomic clocks on Earth. Some millisecond pulsars are so stable that they can be used as cosmic clocks, allowing astronomers to study subtle effects like gravitational waves and the motions of the solar system through space. The timing precision is so extraordinary that changes in pulse arrival times of just a few nanoseconds can be detected and analyzed. Pulsars also provide unique laboratories for testing our understanding of physics under extreme conditions. The strong gravitational fields around pulsars allow us to test Einstein's theory of general relativity with unprecedented precision. Binary pulsars, where two neutron stars orbit each other, have provided some of the most stringent tests of general relativity ever performed. The orbital decay of these systems due to gravitational wave emission has been measured with such precision that it provided the first indirect evidence for gravitational waves decades before they were directly detected. The study of pulsar timing has revealed that neutron stars are not perfectly smooth, uniform objects. Occasionally, pulsars experience sudden increases in their rotation rate called glitches. These events are thought to be caused by the neutron star's crust, cracking and readjusting as the star spins down. The study of these glitches provides insights into the structure and composition of neutron star crusts and the exotic matter they contain. Different types of pulsars emit radiation at different wavelengths, from radio waves to gamma rays. Radio pulsars are the most common and were the first to be discovered. X-ray pulsars often occur in binary systems where material from a companion star falls onto the neutron star's surface, heating it to millions of degrees. Gamma-ray pulsars emit the most energetic radiation, with individual photons carrying more energy than the most powerful particle accelerators on Earth can produce. The population of known pulsars now includes more than 3,000 objects, each with its own unique characteristics. Some pulsars are isolated objects spinning down slowly over millions of years. Others are in binary systems, either with normal stars or with other neutron stars or white dwarf stars. The diversity of pulsar systems provides astronomers with a rich laboratory for studying neutron star physics under a wide range of conditions. The precision timing of pulsars has applications beyond basic physics research. Arrays of millisecond pulsars are being used to search for gravitational waves from supermassive black hole mergers. The concept, called pulsar timing arrays, involves monitoring the arrival times of pulses from dozens of pulsars simultaneously. Gravitational waves passing through the solar system would cause tiny correlated changes in the arrival times of pulses from different pulsars, providing a way to detect gravitational waves with wavelengths much longer than those detectable by ground-based interferometers. The study of pulsars continues to reveal new aspects of neutron star physics. Recent discoveries include pulsars with extremely strong magnetic fields, pulsars in exotic binary systems, and pulsars that switch between different emission modes. Each new discovery adds to our understanding of how matter behaves under the most extreme conditions in the universe and pushes the boundaries of our knowledge about the fundamental laws of physics. As we've seen, neutron stars possess properties so extreme that they challenge our everyday understanding of how the universe works. Their incredible density, magnetic fields, rotation rates, and the lighthouse beams of pulsars represent physics pushed to its absolute limits. But these extreme surface properties are just the beginning of the story. To truly understand what makes neutron stars so remarkable, we must journey deeper, layer by layer, toward their mysterious cores, where the very nature of matter itself may be transformed into something unrecognizable. Chapter 3. Journey to the Core. The structure of a neutron star. To truly understand what makes neutron stars so extraordinary, we need to journey from their surface down to their mysterious core. This isn't just a casual trip through different layers of matter, it's a descent through increasingly alien realms where the fundamental rules of physics become progressively more extreme. Each layer we encounter challenges our understanding of how matter can behave under conditions that simply don't exist anywhere else in the observable universe. The structure of a neutron star resembles an onion, with each concentric layer possessing dramatically different properties from the one above it. As we move deeper into the star, we encounter matter in states that become increasingly exotic and difficult to comprehend. The journey takes us through densities that start at merely 1,000,000 times denser than water and climb to levels that exceed the density of atomic nuclei themselves. What makes this exploration particularly fascinating is that each layer represents a different regime of physics. Near the surface we can still apply familiar concepts from solid-state physics, though pushed to extraordinary extremes. But as we venture deeper, we enter territories where quantum mechanics dominates, where matter behaves in ways that seem to violate common sense, and where the very particles that make up ordinary matter begin to transform into something entirely different. The total journey from surface to center covers only about 6 miles, roughly the distance you might walk to the local grocery store. Yet this short distance encompasses some of the most extreme gradients in density, pressure and temperature found anywhere in the universe. The changes in physical conditions are so dramatic that matter literally transforms from one state to another as we descend through each layer. Understanding the internal structure of neutron stars requires us to think beyond our everyday experience with matter. On Earth, we're familiar with how materials behave under various conditions, how water freezes into ice, how metals can be compressed or stretched, how gases expand when heated. But neutron stars operate in a regime where these familiar concepts become completely inadequate. We're dealing with matter compressed to densities where the normal rules of chemistry and even atomic physics begin to break down. The key to comprehending neutron star structure lies in understanding how matter responds to pressure. As pressure increases, matter undergoes a series of phase transitions, similar to how water turns to ice under certain conditions, but far more dramatic. Each phase transition marks the boundary between different layers of the neutron star, and each new phase represents matter in a state that becomes increasingly removed from anything we encounter in our daily lives. The pressures involved are so extreme that they can only be described in terms that sound almost fictional. The pressure at the center of a neutron star is roughly 10 times greater than the pressure at the center of an atomic nucleus. To put this in perspective, if you could somehow create a pressure vessel capable of withstanding such forces, it would need walls made of a material stronger than anything that exists on Earth. And those walls would need to be thicker than the distance from Earth to the Moon. The crust, a rigid shell of neutrons. Our journey begins at the surface of the neutron star, where we encounter the outermost layer known as the crust. Despite being called a surface, this region is unlike any surface we know on Earth. The crust extends down to a depth of about 1 mile, representing roughly 1/6 of the neutron star's total radius. While this might seem like a thin shell, it contains more mass than our entire moon. The outermost portion of the crust, sometimes called the outer crust, consists of a solid, crystalline lattice of atomic nuclei embedded in a sea of electrons. But these aren't ordinary atomic nuclei. The extreme gravitational field of the neutron star has compressed matter to such a degree that only the most stable neutron-rich nuclei can exist. The typical nuclei found in the outer crust contain far more neutrons than protons compared to the atoms we encounter on Earth. As we descend deeper into the crust, the composition becomes increasingly exotic. The pressure rises steadily, forcing more and more protons to capture electrons and transform into neutrons. This process, known as electron capture, gradually shifts the nuclear composition toward ever more neutron-rich isotopes. Many of these isotopes don't exist naturally on Earth and can only be created artificially in particle accelerators, where they survive for mere fractions of a second before decaying. The density in the outer crust starts at about 1 million times the density of water and increases rapidly with depth. To help you grasp these numbers, imagine taking a sugar cube and somehow packing it with the mass of 1,000 cars. That's the kind of density we're dealing with in the outer regions of the neutron star crust. The matter is so compressed that the distance between atomic nuclei becomes comparable to the size of the nuclei themselves. What makes the crust particularly fascinating is its mechanical properties. Despite being composed of matter in an extremely exotic state, the crust behaves like an incredibly strong solid. The crystalline lattice of nuclei creates a material that is roughly 10 billion times stronger than steel. This extraordinary strength comes from the fact that the nuclei are packed so tightly together that they form an almost perfect crystal structure, with each nucleus locked in place by the electromagnetic forces from its neighbors. The strength of neutron star crust material is so extreme that it could theoretically support a mountain roughly 10 billion times taller than Mount Everest before the material would begin to deform under its own weight. This incredible strength plays a crucial role in the behavior of neutron stars, allowing them to maintain their shape even while spinning at phenomenal speeds that would tear apart any ordinary material. As we continue our descent through the crust, we encounter the neutron drip line, a critical boundary where the composition of matter undergoes a fundamental change. Beyond this point, the nuclei become so neutron-rich that they can no longer hold all their neutrons. Free neutrons begin to drip out of the nuclei, creating a mixture of neutron-rich nuclei, electrons, and free neutrons. This marks the transition from the outer crust to the inner crust. The inner crust represents an even more exotic state of matter. Here the free neutrons that have dripped out of the nuclei form a quantum fluid that coexists with the crystalline lattice of nuclei. This creates a bizarre dual-phase system where we have both a solid component, the nuclear lattice, and a liquid component, the free neutrons, occupying the same space. The neutrons in this region begin to exhibit quantum mechanical behaviors that are completely alien to our everyday experience. The density in the inner crust continues to climb, reaching levels that approach the density of atomic nuclei themselves. At these densities, the distinction between individual nuclei begins to blur. The nuclei become so large and so closely packed that they begin to touch one another, creating strange geometric shapes that have been dubbed nuclear pasta by physicists. These pasta-like structures include rod-like formations called spaghetti, sheet-like formations called lasagna, and various other complex three-dimensional shapes. The nuclear pasta phase represents one of the most unusual states of matter predicted to exist anywhere in the universe. The nuclei are no longer spherical, but have been stretched and deformed into these exotic shapes by the extreme conditions. The transitions between different pasta phases may create interfaces that are incredibly difficult for neutrons to penetrate, potentially affecting how heat and electrical current flow through the neutron star. Throughout the crust, temperature plays a crucial role in determining the exact properties of matter. Newly formed neutron stars are born with temperatures of billions of degrees, hot enough that thermal effects compete with the quantum mechanical forces that determine the structure of matter. As the neutron star cools over millions of years, the matter in the crust settles into increasingly ordered crystalline structures. Much like how a liquid metal solidifies as it cools, but under conditions far more extreme than anything we can create on Earth. The magnetic field of the neutron star also influences the structure of the crust. The incredibly strong magnetic field can actually change the shape of atoms, stretching electron orbitals into cigar-like shapes and creating magnetic domains within the crystalline lattice. In the most magnetized neutron stars, called magnetars, the magnetic field is so strong that it can stress the crust material to the point of fracturing, creating starquakes that release more energy than the largest earthquakes on Earth. The crust also serves as the neutron star's primary heat reservoir. The thermal energy stored in the crust determines how quickly the neutron star cools and how its surface temperature changes over time. Understanding the thermal properties of crust material is crucial for interpreting observations of neutron star surface temperatures and inferring the age and thermal history of these objects. The outer core, a sea of superfluid neutrons. As we penetrate deeper into the neutron star, we cross a boundary that marks one of the most dramatic transitions in the entire structure, the interface between the crust and the outer core. This boundary, located at a density roughly equivalent to the density of atomic nuclei, represents the point where individual nuclei finally disappear entirely. Beyond this point, we enter a realm dominated by free neutrons, protons, and electrons existing in a state of matter that has no analogue anywhere else in the universe. The outer core extends from the base of the crust down to roughly half the neutron star's radius. This region contains the majority of the neutron star's mass and represents matter in a state that pushes the boundaries of nuclear physics. The density here starts at about 100 million tons per cubic centimetre and increases steadily as we move toward the centre. To put this in perspective, a thimble full of outer core material would weigh as much as a mountain. What makes the outer core truly extraordinary is that the neutrons here exist in a superfluid state. Superfluidity is a quantum mechanical phenomenon where a fluid flows without any viscosity or resistance whatsoever. On Earth, we can observe superfluidity in liquid helium cooled to temperatures near absolute zero, but in neutron stars, the extreme conditions create superfluidity at temperatures of millions of degrees. The superfluid nature of neutron star matter has profound implications for how these objects behave. In a normal fluid, friction and viscosity cause moving currents to gradually slow down and dissipate their energy as heat. But in a superfluid, currents can persist indefinitely without any energy loss. This means that once set in motion, the superfluid neutrons in the outer core can maintain their flow patterns for millions of years. The transition to superfluidity occurs because neutrons, like electrons, are fermions, particles that obey the Pauli exclusion principle. At the extreme densities found in neutron star cores, neutrons begin to pair up in a process similar to how electrons form Cooper pairs in superconductors. These neutron pairs, called Cooper pairs, behave as composite particles that can occupy the same quantum state, leading to the superfluid behavior. Understanding neutron superfluidity requires us to think about quantum mechanics on a macroscopic scale. While quantum effects are usually confined to the microscopic world of atoms and subatomic particles, the extreme conditions in neutron star cores create a situation where quantum mechanical phenomena dominate the behavior of matter on astronomical scales. The entire outer core of a neutron star behaves as a single giant quantum mechanical system. The superfluid properties of the outer core have observable consequences for neutron star behavior. One of the most dramatic examples is the phenomenon known as a glitch. Occasionally, astronomers observe a sudden increase in the rotation rate of a pulsar, as if the star suddenly sped up. These glitches are thought to result from the complex interaction between the superfluid neutrons in the core and the normal matter in the crust. The mechanism behind pulsar glitches involves the concept of quantized vortices in the superfluid. Just as a figure skater spins faster when they pull in their arms, a contracting neutron star should spin faster to conserve angular momentum. However, the superfluid neutrons in the core can maintain their original rotation rate while the crust spins up, creating a situation where the core and crust rotate at different speeds. This differential rotation creates stress in the neutron star, stored in the form of quantized vortices in the superfluid. These vortices are like tiny tornadoes in the neutron fluid, each carrying a fixed amount of angular momentum. As the stress builds up, the vortices eventually undergo a sudden rearrangement, transferring angular momentum from the superfluid core to the crust and causing the observed glitch in the pulsar's rotation rate. The outer core also contains a small but significant population of protons and electrons. While neutrons make up roughly 95% of the particles in this region, the remaining 5% consists of protons and electrons that exist in a delicate balance determined by the requirement of electrical neutrality. The protons in the outer core also form a superfluid, but with different properties from the neutron superfluid. The protons in the outer core can also form Cooper pairs, but these pairs have different binding energies and transition temperatures compared to the neutron pairs. This creates a complex, multi-component superfluid system where different types of particles can flow independently of each other. The interaction between these different superfluid components adds another layer of complexity to neutron star physics. The electrons in the outer core behave quite differently from the neutrons and protons. Due to their much smaller mass, electrons in the outer core are highly relativistic, meaning they move at speeds approaching the speed of light. These relativistic electrons form what's called a degenerate electron gas, where quantum mechanical effects completely dominate their behavior. The pressure contributed by these relativistic electrons plays a crucial role in supporting the neutron star against gravitational collapse. The outer core is also where we begin to encounter the effects of the strong nuclear force on macroscopic scales. The nuclear force, which binds protons and neutrons together in atomic nuclei, typically operates only over distances comparable to the size of a proton. But at the extreme densities found in neutron star cores, particles are packed so tightly that the strong force begins to influence the overall structure and stability of the star. The equation of state, the relationship between pressure, density and temperature, becomes increasingly uncertain as we move deeper into the outer core. While we have a reasonable understanding of how matter behaves at nuclear densities, the conditions in neutron star cores push beyond the regime where our theories have been thoroughly tested. This uncertainty is one of the driving forces behind current research in neutron star physics. The outer core also plays a crucial role in determining the neutron star's magnetic field structure. The movement of charged particles, particularly protons, through the superfluid neutron medium can generate and maintain the strong magnetic fields observed in neutron stars. The interplay between superfluidity and magnetic fields creates complex dynamics that are still not fully understood. Temperature continues to play an important role in outer core physics, though the superfluid transitions occur at much higher temperatures than those observed in terrestrial superfluids. The critical temperature for neutron superfluidity in the outer core is estimated to be around 100 million Kelvin, which means that even very young, hot neutron stars likely contain superfluid regions. The inner core, where physics breaks down. As we approach the very center of the neutron star, we enter the most mysterious and exotic region of all, the inner core. This innermost region, which may extend from about half the neutron star's radius down to the center, represents the ultimate frontier of high-density physics. Here, at densities that exceed the density of atomic nuclei by factors of 3 to 10, we encounter conditions so extreme that our current understanding of physics begins to break down entirely. The inner core is where the fundamental nature of matter itself may undergo transformations that are impossible to study in any terrestrial laboratory. The densities here are so extreme that they can only be approached in the most energetic particle accelerator experiments, and even then, only for fleeting instants measured in fractions of a second. In neutron star cores, these conditions persist for millions of years, creating a natural laboratory for studying matter under conditions that represent the absolute limits of what the universe allows. At the densities found in neutron star inner cores, the traditional picture of matter composed of protons, neutrons and electrons begins to break down. The particles that make up ordinary matter may no longer exist as distinct entities. Instead, they may dissolve into their more fundamental constituents or transform into entirely new types of particles that don't exist anywhere else in the present-day universe. One of the most intriguing possibilities for inner core composition involves the appearance of hyperons, strange cousins of ordinary protons and neutrons. Hyperons are particles that contain strange quarks, one of the 6 types of quarks that make up the fundamental building blocks of matter. Under normal conditions, hyperons are highly unstable and decay almost immediately after being created. But the extreme conditions in neutron star cores may stabilize these exotic particles, allowing them to exist in significant numbers. The presence of hyperons in neutron star cores would have profound implications for our understanding of these objects. Hyperons are generally less massive than neutrons, which means their appearance would soften the equation of state. the relationship between pressure and density that determines how matter responds to compression. This softening could affect the maximum possible mass of a neutron star and influence how these objects behave during collisions or other extreme events. Even more exotic is the possibility that matter in neutron star cores might undergo a phase transition to quark matter. Quarks are the fundamental particles that make up protons and neutrons, normally confined within these larger particles by the strong nuclear force. But at the extreme densities found in neutron star cores, the boundaries between individual protons and neutrons may completely disappear, releasing the quarks to form a new state of matter called quark matter. Quark matter would represent a return to conditions that existed in the universe during the first few microseconds after the Big Bang, when temperatures and densities were so extreme that quarks existed freely rather than being confined within protons and neutrons. The transition to quark matter would be one of the most dramatic phase transitions possible, fundamentally altering the nature of matter from particles with internal structure to a soup of truly elementary constituents. The behavior of quark matter is governed by quantum chromodynamics, the theory that describes the strong nuclear force. At extreme densities, quarks may form a color superconductor, where quarks of different colors pair up in a manner analogous to Cooper pairs in superconductors. This would create a state of matter with properties unlike anything we observe in the everyday world. The possibility of quark matter in neutron star cores has led to speculation about the existence of strange stars, objects that are composed entirely of strange quark matter rather than ordinary nuclear matter. Strange stars would be even more compact than neutron stars, with surface densities comparable to nuclear density. The surface of a strange star would be unlike anything we can imagine, potentially containing a crystalline crust of strange matter with properties that challenge our understanding of solid-state physics. Another exotic possibility for inner core composition involves the creation of kaon condensites. Kaons are particles that contain strange quarks and normally decay very quickly. But at high densities, kaons might form a Bose-Einstein condensate, where many kaons occupy the same quantum state. This would create another form of exotic matter with properties that are completely different from anything found in ordinary nuclear matter. The uncertainties in inner core physics are so profound that we cannot even be certain whether neutron stars have discrete inner cores or whether the properties of matter change continuously from the outer core to the center. The phase transitions that might occur in the inner core could be gradual crossovers rather than sharp boundaries, making it difficult to define where one phase ends and another begins. These uncertainties have direct observational consequences. The equation of state in the inner core determines crucial properties of neutron stars, including their maximum possible mass, their radius for a given mass, and their response to deformation. Different possibilities for inner core composition predict different relationships between mass and radius, which can be tested through careful observations of neutron star properties. The inner core also plays a crucial role in determining how neutron stars cool over time. Different types of exotic matter have different thermal properties and different mechanisms for generating or absorbing heat. The presence of hyperons, quarks, or other exotic particles could dramatically alter the cooling rate of neutron stars, providing another way to constrain the composition of these extreme objects. Magnetic fields in the inner core face additional complications from the exotic matter that might exist there. The magnetic properties of hyperon matter or quark matter are largely unknown, but they could be very different from those of ordinary nuclear matter. The interaction between strong magnetic fields and exotic matter states represents one of the most complex problems in modern theoretical physics. The inner core is also where general relativistic effects become most pronounced. The extreme densities and gravitational fields in the inner core create conditions where space and time themselves are significantly curved. This curvature affects the behavior of matter and energy in ways that are still being explored by theorists. The interplay between exotic matter states and strong gravitational fields creates a regime of physics where quantum mechanics and general relativity must be considered simultaneously. Understanding the inner core requires pushing the boundaries of multiple fields of physics simultaneously. Nuclear physics, particle physics, quantum field theory, and general relativity all play crucial roles in determining the properties of matter under these extreme conditions. The inner core represents a natural laboratory for testing our most fundamental theories of physics under conditions that cannot be reproduced anywhere else. The mystery of neutron star inner cores drives some of the most ambitious observational programs in modern astronomy. Space-based missions like the Neutron Star Interior Composition Explorer have been designed specifically to peer inside these objects. Ground-based gravitational wave detectors have opened up entirely new ways of studying neutron star collisions. Advanced computer simulations now allow us to model the behavior of matter under conditions that exist nowhere else in the universe. As we stand on the threshold of revolutionary discoveries about neutron stars, we're about to embark on a journey that will take us from the explosive deaths of massive stars to the very heart of matter itself. We'll explore how these cosmic laboratories challenge our understanding of physics, reveal the existence of exotic forms of matter that may not exist anywhere else in the universe, and provide insights into the fundamental nature of reality itself. The story of neutron stars is ultimately a story about the limits of physics and the incredible creativity of the universe in pushing matter and energy to their absolute extremes. These objects represent nature's most successful attempt to compress as much mass as possible into the smallest possible space without creating a black hole. They're cosmic experiments in the behavior of matter under conditions so extreme that they stretch our theories to their breaking point. In the following chapters, we'll peel back the layers of these cosmic enigmas, starting with their violent birth in supernova explosions and working our way down to their mysterious cores, where the very nature of matter itself may be transformed into something unrecognizable. We'll discover how neutron stars have become cosmic laboratories that are helping us understand everything from the behavior of matter at nuclear densities to the nature of space and time itself. The journey ahead will challenge everything you think you know about the physical world. We'll encounter matter so dense it defies imagination, magnetic fields that could tear apart atoms, and rotation speeds that push the very fabric of space-time to its limits. By the end of this exploration, you'll understand why neutron stars represent some of the most extreme and fascinating objects in the entire universe, and why their secrets continue to drive the cutting edge of modern physics. Chapter 4. The Ultimate Mystery: Exotic States of Matter. We've journeyed through the outer layers of neutron stars, witnessed their incredible density, and explored the superfluid neutron ocean that flows within their outer core. But now we arrive at the most mind-bending destination of all. The inner sanctum where the fundamental building blocks of reality itself may be transformed into something completely alien to our everyday experience. Deep within the heart of a neutron star, where pressures exceed anything found elsewhere in the universe, matter doesn't just behave strangely. It becomes something entirely different. The conditions here are so extreme that they haven't existed anywhere in the cosmos since the first microseconds after the Big Bang. We're talking about pressures that are 5 to 10 times greater than the density of atomic nuclei themselves. To understand what happens under these conditions, we need to grasp just how extraordinary the environment becomes. The pressure at the center of a neutron star reaches approximately 500 million tons per square inch. If you could somehow place a single atom at the center of a neutron star, it would experience a crushing force equivalent to the weight of Mount Everest, pressing down on an area smaller than the period at the end of this sentence. Under such incomprehensible conditions, the very nature of matter begins to break down and transform. The neutrons that give these stars their name can no longer maintain their individual identity. Instead, they begin to dissolve into their constituent parts, revealing layers of reality that exist nowhere else in the modern universe. Hyperons and strange matter, particles beyond protons and neutrons. The first transformation we encounter as we dive deeper into the neutron star core involves the creation of particles that don't exist naturally anywhere on Earth. These exotic particles, called hyperons, represent the next step beyond ordinary protons and neutrons in the hierarchy of matter. Hyperons are fundamentally different from the familiar particles that make up everything we know. While protons and neutrons belong to a family called baryons, hyperons are their strange cousins, literally containing quarks with the property called strangeness. Under the crushing pressures found in neutron star cores, ordinary neutrons begin to transform into lambda hyperons, sigma hyperons, and cascade hyperons. The creation of hyperons happens through a process that defies our everyday understanding of stability. On Earth, hyperons are incredibly short-lived particles that decay almost instantly after being created in high-energy collisions. A lambda hyperon, for example, exists for only about 200 picoseconds before decaying back into familiar particles. But inside a neutron star, the extreme pressure and density create conditions where hyperons can become stable and form a significant portion of the star's composition. The presence of hyperons fundamentally changes the equation of state, the relationship between pressure and density that determines the neutron star's structure. When hyperons begin to appear, they soften the matter, making it more compressible. This might seem counterintuitive, but the reason lies in the quantum mechanical properties of these particles. Hyperons provide additional degrees of freedom for the system, allowing the matter to achieve lower energy states at high densities. The formation of hyperon matter represents a phase transition as dramatic as water turning to ice, but occurring under conditions that are millions of times more extreme. As the density increases beyond about 4 times nuclear density, neutrons begin spontaneously converting into hyperons. This process releases energy and creates a cascade effect where more and more hyperons are produced. Recent theoretical calculations suggest that hyperons may begin appearing when the density reaches approximately 600 million tons per cubic inch. At this point, the neutron star's core becomes a hyperon soup, a state of matter that combines ordinary neutrons with these exotic particles in proportions that depend on the exact conditions present. The implications of hyperon formation extend far beyond theoretical physics. The presence of hyperons affects the neutron star's maximum possible mass. If hyperons soften the matter too much, neutron stars might collapse into black holes at lower masses than previously thought. This creates what physicists call the hyperon puzzle, reconciling the existence of very massive neutron stars with theories that predict hyperon formation should make such massive objects impossible. Quark matter, when subatomic particles break free. As we venture even deeper into the neutron star's core, we encounter conditions so extreme that even hyperons cannot maintain their integrity. The pressure becomes so intense that the individual particles themselves begin to dissolve, revealing the fundamental building blocks from which all matter is constructed: quarks. Quarks represent the deepest level of matter that we currently understand. They're the constituent particles that make up protons and neutrons, bound together by the strong nuclear force through particles called gluons. Under normal circumstances, quarks are permanently confined within larger particles and cannot exist independently. But the core of a neutron star may provide the only environment in the modern universe where quarks can break free from this confinement. The transition from ordinary matter to quark matter represents one of the most profound phase transitions possible in physics. When the pressure reaches approximately 10 times the density of atomic nuclei, the boundaries between individual neutrons and hyperons begin to dissolve. The quarks that were once confined within these particles suddenly find themselves free to move throughout the entire volume of the neutron star's core. This creates what physicists call a quark-gluon plasma, a state of matter that last existed throughout the universe during the first few microseconds after the Big Bang. In this state, quarks and gluons move freely without being bound into larger particles. The matter becomes a soup of fundamental particles swimming in a sea of the strong force itself. The properties of quark matter are almost impossible to comprehend using our everyday experience. The matter becomes essentially massless at the quark level, with the mass of the neutron star being carried almost entirely by the energy stored in the strong force fields that permeate the core. The quarks themselves move at speeds approaching the speed of light, creating a relativistic quantum fluid unlike anything found elsewhere in nature. The formation of quark matter might occur through a process called deconfinement, where the strong force that normally binds quarks together becomes so diluted by the high density that it effectively disappears. Alternatively, the transition might happen gradually, with quarks slowly becoming more mobile as the density increases until suddenly they achieve complete freedom of movement. One of the most intriguing possibilities is that quark matter might be absolutely stable, more stable than ordinary atomic matter. If this is the case, then the core of a neutron star might represent the true ground state of matter, with everything else in the universe existing in a metastable state that could theoretically decay into quark matter given the right conditions. The strange matter hypothesis suggests that quark matter composed of up, down, and strange quarks might be the most stable form of matter in the universe. If this is true, then neutron stars might actually be strange stars, objects composed almost entirely of strange quark matter with only a thin crust of ordinary matter on their surface. The observational signatures of quark matter are subtle but potentially detectable. The equation of state of quark matter is stiffer than that of ordinary neutron matter, which means that neutron stars with quark cores might be able to achieve higher maximum masses. The transition to quark matter might also affect the star's cooling rate, as quarks can emit neutrinos through processes that aren't available to ordinary matter. The quest for knowledge, current research and future missions. The search for exotic matter in neutron stars represents one of the most ambitious scientific endeavors of our time. Scientists are using every tool at their disposal to peer inside these cosmic laboratories and determine what forms of matter actually exist under such extreme conditions. The Neutron Star Interior Composition Explorer, known as NISA, has revolutionized our ability to study neutron star interiors. This X-ray telescope, mounted on the International Space Station, measures the precise timing of X-ray pulses from neutron stars with unprecedented accuracy. By analyzing how these pulses change as the neutron star rotates, scientists can map the star's shape and infer properties of its interior composition. NISA's observations have already provided crucial insights into neutron star structure. The telescope has measured the masses and radii of several neutron stars with remarkable precision, providing the first direct constraints on the equation of state of matter at nuclear densities. These measurements suggest that neutron star matter is stiffer than many theoretical models predicted, which has important implications for the possible existence of exotic matter in their cores. Gravitational wave astronomy has opened up an entirely new window into neutron star physics. When two neutron stars spiral into each other and merge, they create ripples in space-time that can be detected by observatories like LIGO and Virgo. The pattern of these gravitational waves carries information about the star's internal structure, including the stiffness of their matter. The 2017 detection of gravitational waves from the neutron star merger GW170817 provided the first direct measurement of the neutron star equation of state through gravitational wave astronomy. The event showed that neutron star matter becomes stiffer at high densities, which constrains the possible forms of exotic matter that might exist in their cores. Advanced computer simulations are pushing the boundaries of our theoretical understanding. Scientists are using supercomputers to model the behavior of matter under neutron star conditions, incorporating the latest understanding of quantum chromodynamics, the theory that describes the strong nuclear force. These simulations are revealing new possibilities for exotic matter states and helping to interpret observational data. The field of lattice quantum chromodynamics has made remarkable progress in recent years. By discretizing space-time and using powerful computers to solve the equations of the strong force, scientists can calculate the properties of quark matter from first principles. These calculations are beginning to converge on consistent predictions for the behavior of matter at extreme densities. Future missions promise to revolutionize our understanding even further. The proposed enhanced X-ray timing and polarimetry mission would provide even more precise measurements of neutron star properties. Ground-based gravitational wave detectors are being upgraded to detect neutron star mergers from much greater distances, providing larger samples for statistical analysis. The James Webb Space Telescope is beginning to observe the aftermath of neutron star mergers, studying the heavy elements produced in these events and providing insights into the nuclear processes that occur when exotic matter is disrupted. These observations are revealing the role that neutron stars play in creating the elements that make up planets and life itself. Laboratory experiments are also contributing to our understanding of exotic matter. High-energy particle accelerators like the Large Hadron Collider create conditions similar to those found in neutron star cores, allowing scientists to study the properties of quarks and gluons under extreme conditions. These experiments are providing crucial input for theoretical models of neutron star matter. The quest to understand neutron star interiors is driving innovations in theoretical physics as well. Scientists are developing new mathematical frameworks to describe the behavior of matter under extreme conditions, incorporating insights from string theory, holographic duality, and other advanced theoretical approaches. One of the most exciting frontiers is the study of neutron star oscillations. Just as seismic waves reveal the internal structure of Earth, oscillations in neutron stars could provide direct information about their internal composition. These starquakes, caused by sudden rearrangements of the neutron star's crust or core, create detectable changes in the star's rotation that could reveal the presence of exotic matter. The search for axions and other dark matter candidates is also being conducted using neutron stars. These hypothetical particles might be produced in neutron star cores and could affect the star's cooling rate or magnetic field evolution. Detecting these effects could provide the first direct evidence for physics beyond the standard model. As we stand on the threshold of revolutionary discoveries, neutron stars continue to challenge our understanding of the fundamental nature of matter and energy. These cosmic laboratories are testing our theories under conditions that cannot be replicated anywhere else, pushing the boundaries of physics and revealing new possibilities for the behavior of matter under extreme conditions. The ultimate goal of this research is not just to understand neutron stars themselves, but to use them as probes of fundamental physics. By studying how matter behaves under the most extreme conditions in the universe, we're gaining insights into the deepest laws of nature and the fundamental structure of reality itself. The answers we seek about neutron star interiors will ultimately tell us whether our current theories of physics are complete, or whether entirely new physics awaits discovery in the hearts of these cosmic enigmas. Each new observation brings us closer to understanding whether exotic matter states actually exist in nature and what they might tell us about the fundamental building blocks of the universe. Chapter 5. Neutron Stars. Windows to the Cosmos. Neutron stars have evolved from mysterious cosmic curiosities into the most powerful scientific instruments the universe has ever provided. These stellar remnants serve as natural laboratories where the most extreme physics experiments are conducted on scales impossible to replicate on Earth. The data streaming from these cosmic laboratories is revolutionizing our understanding of fundamental physics, cosmology, and the very nature of matter itself. The transformation of neutron stars from astronomical oddities to scientific gold mines began with a revolutionary discovery that changed physics forever. When scientists first detected gravitational waves in 2015, they opened an entirely new window into the universe. These ripples in space-time itself, predicted by Einstein over a century ago, were finally captured by the most sensitive instruments ever built. The detection marked the beginning of gravitational wave astronomy, and neutron stars would soon become the stars of this new field. Gravitational waves. Ripples from neutron star collisions. The concept of gravitational waves emerges from Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of space-time itself. When massive objects accelerate through space, they create ripples in this fabric of space-time that propagate outward at the speed of light. Think of space-time as a stretched rubber sheet, and massive accelerating objects as bowling balls rolling around on that sheet, creating waves that spread outward from their motion. For decades, detecting these waves remained one of the greatest challenges in experimental physics. The waves are incredibly weak by the time they reach Earth, causing distortions in space that are smaller than 1/10,000th the width of a proton. To detect such minute changes, scientists built the Laser Interferometer Gravitational Wave Observatory, or LIGO, which uses laser beams travelling down 4-kilometre-long arms to measure changes in distance with unprecedented precision. The first gravitational waves detected came from black hole collisions, but the real breakthrough for neutron star science came on August 17, 2017. On that day, LIGO detected gravitational waves from an event unlike any previously observed. The signal, designated GW170817, showed the characteristic pattern of two neutron stars spiraling toward each other in a cosmic dance of destruction that had been playing out for millions of years. The neutron-star merger that produced GW170817 began when two neutron stars, each containing more mass than our Sun packed into a sphere the size of a city, found themselves locked in a decaying orbit around each other. As they spiraled inward, they moved faster and faster, their immense gravitational fields creating increasingly powerful waves in space-time. The waves carried away energy from the system, causing the stars to spiral ever closer together. During the final moments before collision, the neutron stars were orbiting each other hundreds of times per second. The gravitational waves they produced swept across the cosmos, carrying information about the mass, spin, and internal structure of the stars. When the waves reached Earth after traveling 130 million light-years, they caused the arms of the LIGO detectors to stretch and compress by distances smaller than the nucleus of an atom. The collision itself lasted only milliseconds, but it released more energy than our Sun will produce over its entire 10-billion-year lifetime. The impact shattered both neutron stars, creating a kilonova explosion that briefly outshone every star in its host galaxy. The explosion ejected massive amounts of neutron-rich material into space, creating conditions perfect for rapid neutron capture nucleosynthesis. What makes gravitational wave detections so revolutionary is the unprecedented information they provide about neutron star interiors. The waves carry detailed information about the equation of state of nuclear matter, essentially how matter behaves under the extreme conditions found inside neutron stars. By analyzing the gravitational wave signals, scientists can determine how easily neutron stars deform under gravitational stress, which directly relates to the stiffness of matter at nuclear densities. The analysis of GW170817 revealed that neutron stars are less deformable than some theoretical models predicted, placing important constraints on the equation of state of nuclear matter. This information is crucial for understanding what happens to matter when it's compressed to densities exceeding those found in atomic nuclei. The data suggests that neutron stars maintain their integrity even under extreme gravitational stress, indicating that nuclear matter becomes increasingly resistant to compression at the highest densities. Gravitational wave astronomy has also provided new insights into the population of neutron stars in the universe. By detecting mergers at different distances, scientists can estimate how frequently these events occur and how they contribute to the overall evolution of galaxies. The rate of neutron star mergers has implications for understanding stellar evolution, supernova rates, and the chemical evolution of the universe. The future of gravitational wave astronomy looks incredibly promising. Next-generation detectors currently under construction will be 10 times more sensitive than current instruments, allowing scientists to detect neutron star mergers throughout the observable universe. These enhanced capabilities will provide thousands of neutron star merger detections, creating a statistical sample large enough to map the equation of state of nuclear matter with unprecedented precision. Forging the elements, how neutron stars create gold and platinum. The story of how neutron stars create the heaviest elements in the universe begins with understanding the fundamental process of nucleosynthesis, the creation of atomic nuclei through nuclear reactions. During the normal lifetime of a star, nuclear fusion reactions in the stellar core create elements up to iron and nickel. However, creating elements heavier than iron requires conditions so extreme that they can only be found in the most catastrophic cosmic events. The process responsible for creating gold, platinum, uranium, and other heavy elements is called rapid neutron capture nucleosynthesis, or the R process. This process requires an environment with an incredibly high density of free neutrons, temperatures exceeding 100 million degrees Kelvin, and timescales shorter than the radioactive decay times of unstable nuclei. Until recently, scientists weren't entirely sure where in the universe such extreme conditions could be found. The answer came with the detection of GW 170817 and the subsequent optical observations of the kilonova explosion it produced. When two neutron stars collide, they create exactly the conditions needed for R-process nucleosynthesis. The collision ejects massive amounts of neutron-rich material into space, creating an environment where atomic nuclei can rapidly capture neutrons faster than they can radioactively decay. During the first few seconds after a neutron star merger, the ejected material undergoes a complex series of nuclear reactions. Neutron-rich nuclei absorb neutrons in rapid succession, building up increasingly heavy elements. The process is so efficient that it can create elements with atomic masses exceeding 200 in just a few seconds. These super-heavy nuclei then undergo radioactive decay, gradually transforming into stable heavy elements like gold, platinum, and rare earth metals. The amount of gold produced in a single neutron star merger is staggering. The collision that produced GW 170817 created approximately 10 Earth masses of gold, along with 100 Earth masses of platinum and similar amounts of other precious metals. To put this in perspective, all the gold that has ever been mined on Earth throughout human history amounts to less than 200,000 tons, which represents only a tiny fraction of what was created in that single cosmic event. The kilonova explosion that follows a neutron star merger is powered by the radioactive decay of the freshly synthesized heavy elements. The initial blue-white light of the explosion comes from the decay of elements like nickel-56, while the later red infrared emission results from the decay of lanthanides and actinides. The characteristic light curve and spectrum of kilonovae provide astronomers with a direct way to observe R-process nucleosynthesis in action. The discovery that neutron star mergers are responsible for producing heavy elements has solved one of the longest-standing mysteries in astrophysics. For decades, scientists knew that core-collapse supernovae could produce elements up to iron, but the origin of elements heavier than iron remained unclear. Some theories suggested that these elements were produced in special types of supernovae, while others proposed that they were created in the cores of massive stars. The observation of kilonova explosions has definitively shown that neutron star mergers are the primary source of R-process elements in the universe. This discovery has profound implications for our understanding of galactic chemical evolution. The heavy elements produced in neutron star mergers are dispersed throughout the galaxy, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. The gold in your jewelry, the platinum in your car's catalytic converter, and the rare earth metals in your smartphone all trace their origins back to neutron star collisions that occurred billions of years ago. The rate of neutron star mergers also explains why heavy elements are relatively rare in the universe. Unlike core collapse supernovae, which occur roughly once per century in a typical galaxy, neutron star mergers happen only once every 10,000 to 100,000 years. This low rate means that heavy elements are gradually enriched in galaxies over cosmic time, explaining why the oldest stars in the universe contain very few heavy elements, while younger stars like our Sun are relatively metal-rich. The study of R-process nucleosynthesis in neutron star mergers has also provided new insights into the physics of nuclear matter under extreme conditions. The efficiency of the R process depends on the nuclear properties of extremely neutron-rich nuclei, many of which have never been produced in laboratory experiments. By comparing the observed abundances of R process elements with theoretical predictions, scientists can test their understanding of nuclear physics far from the valley of stability. The frontier. What neutron stars can teach us about the universe. Neutron stars represent the ultimate testing ground for our most fundamental theories about the nature of reality. These cosmic laboratories provide conditions so extreme that they push the boundaries of quantum mechanics, general relativity, and nuclear physics simultaneously. The insights gained from studying neutron stars are helping to answer some of the most profound questions in modern physics and cosmology. One of the most significant contributions neutron stars make to our understanding of physics is their role as precision tests of general relativity. Einstein's theory of general relativity makes specific predictions about how matter and energy curve spacetime, and neutron stars provide the perfect environment to test these predictions under the most extreme conditions possible. The strong gravitational fields around neutron stars cause time dilation effects so pronounced that clocks on the surface of a neutron star would run roughly 30% slower than clocks on Earth. The orbital decay of binary pulsar systems provides one of the most precise tests of general relativity ever conducted. When two neutron stars orbit each other, they gradually spiral inward as gravitational waves carry away energy from the system. The rate of orbital decay can be predicted with extraordinary precision using Einstein's equations, and observations of systems like the famous Hulse-Taylor pulsar have confirmed these predictions to within 0.2%. This agreement between theory and observation represents one of the most stringent tests of general relativity ever performed. Neutron stars also serve as natural laboratories for studying the behavior of matter under conditions that cannot be replicated on Earth. The densities found in neutron star cores exceed those of atomic nuclei by factors of 2 to 10. Entering a regime where our understanding of nuclear physics becomes increasingly uncertain. The equation of state of nuclear matter at these densities has implications for understanding everything from the properties of atomic nuclei to the behavior of quark matter in the early universe. The study of neutron star mass measurements has revealed important constraints on the equation of state of nuclear matter. The discovery of neutron stars with masses exceeding twice the mass of the Sun has ruled out many theoretical models of nuclear matter, particularly those that predict the existence of exotic phases of matter at relatively low densities. These observations suggest that nuclear matter remains relatively stiff even at the highest densities found in neutron star cores. Neutron stars are also providing new insights into the nature of dark matter, one of the most mysterious components of the universe. Dark matter makes up roughly 27% of the universe's total mass energy, but its nature remains completely unknown. Some theoretical models suggest that dark matter particles could be captured by neutron stars, where they would accumulate in the star's core and potentially affect its observable properties. By studying the thermal evolution, magnetic fields and rotation of neutron stars, scientists are searching for signatures of dark matter interactions. The extreme magnetic fields found around neutron stars are opening new frontiers in our understanding of quantum electrodynamics. In the strongest magnetic fields, the vacuum of space itself becomes polarized, creating conditions where photons can split into electron-positron pairs and where the normal properties of electromagnetic radiation are dramatically altered. These quantum effects are impossible to study in terrestrial laboratories, but are routinely observed in the environments around magnetars. Neutron stars are also contributing to our understanding of the fundamental constants of nature. The properties of neutron stars depend on various physical constants, including the strong nuclear force coupling constant and the mass of the proton. By studying neutron stars at different cosmological distances, scientists can test whether these fundamental constants have remained truly constant over cosmic time. Any variation in these constants would affect the observable properties of neutron stars in ways that could be detected with sufficiently precise observations. The role of neutron stars in testing theories of quantum gravity represents one of the most exciting frontiers in modern physics. The extreme conditions found in neutron star cores may provide the first observational evidence for physics beyond the standard model. Some theories predict that at the highest densities, neutron star matter could undergo phase transitions to exotic forms of matter like quark matter or strange matter, fundamentally changing the star's properties. The study of neutron star timing arrays is opening new possibilities for detecting gravitational waves from supermassive black hole mergers and potentially even from the early universe itself. By precisely monitoring the arrival times of the pulses from dozens of millisecond pulses, scientists are creating a galaxy-sized gravitational wave detector capable of detecting waves with periods of years to decades. This technique could provide evidence for gravitational waves from the merger of supermassive black holes or from cosmic strings left over from the early universe. Neutron stars are also playing a crucial role in our understanding of the universe's large-scale structure and evolution. The population of neutron stars in the galaxy provides information about the history of star formation and the initial mass function of stars. The chemical elements produced in neutron star mergers trace the assembly history of galaxies and the enrichment of the interstellar medium with heavy elements. The future of neutron star science promises even more revolutionary discoveries. New space-based observatories will provide unprecedented views of neutron star surfaces and magnetospheres, while next-generation gravitational wave detectors will detect thousands of neutron star mergers throughout the observable universe. Advanced theoretical work is developing increasingly sophisticated models of neutron star structure and evolution, incorporating the latest advances in nuclear physics and quantum field theory. The study of neutron stars is ultimately teaching us that the universe is far stranger and more wonderful than we ever imagined. These cosmic laboratories are revealing the intimate connections between the smallest scales of nuclear physics and the largest scales of cosmological structure. They're showing us that the universe is capable of creating conditions so extreme that they challenge our most fundamental assumptions about the nature of matter, space, and time itself. As we continue to probe the mysteries of neutron stars, we're not just learning about these remarkable objects themselves. We're gaining insights into the fundamental laws that govern the universe, from the quantum mechanical behavior of matter at the smallest scales to the gravitational dynamics that shape the cosmos on the largest scales. Neutron stars represent the ultimate intersection of physics and astronomy, where the most extreme conditions in the universe provide the clearest windows into the deepest mysteries of existence.